All right, guys. Welcome to another session of Zoom. Welcome all of you. Today is June 16, okay? MENG 260. So I'm going to talk about fluid mechanics, fluid dynamics, or internal and external flow, okay? This topic can be in a semester course, okay? Maybe 2 semesters or maybe 1 semester, possibly it's good. But we're trying to cover this in only 1 or 2 lectures, okay? It's a little bit too much, but it's just part of this introductory to thermal sciences course. Hang in there, everything will be fine, okay? I'm gonna summarize everything for you. So far, we were able to make it and absorb the information and move forward. So one thing you got to remember in internal flow inside the pipe or conduit, you need to know whether the flow is laminar or turbulent or transitional aspect of the flow. The region between the laminar and turbulent, we call it the transitional flow. We need to figure out how do we know which region is laminar, which region is turbulent, and the language of transitional flow. So if you look at the Reynolds number, that is the Reynolds number by definition is rho, density, velocity times diameter of the pipe and times viscosity, or divided by viscosity. So the Reynolds number is dimensionless, okay, value. It has no dimension, it's dimensionless. Based on given properties, and we can just plug it into this formula, and it's going to tell us whether we are in the laminar region or turbulent region. And then the V is the average velocity in the pipe. Okay. People in the past, back in 1900 BI, we used to do the wind tunnel test. We had a lab and fluid mechanics lab with a wind tunnel test. And also we wanted to know whether when we tested the blade or airplane or car to see whether we can reduce the drag. And we just subjected them to wind tunnel. There's a water tunnel, but we call it the wind tunnels, okay? That's a more popular one that we have used in the universities, okay? So they use the smoke. They use the smoke to see whether for the aerodynamics shape, or if you had a box, you could see that the drag is higher. And eventually those fluid mechanics people or dynamics people and the boundary layer theory people wanted to just make the car more energy efficient. So they converted everything from the box or rectangular shape to aerodynamic shaped car that you see, guys. You're lucky, you're very, you're in a generation that you drive a nice car with the, a sporty car aerodynamic shape. So there was a lot of study, a lot of work was done back in 1940s, 50s, 60s, 70s. And I started around 1978, 79. And I used to work with the professor that asked me to do a lot of testing for him. And that's how you learn, okay? If you are working under a professor that has all kinds of equipment and access to tools, so that you learn from the experienced professor, so that you move forward from there. But nowadays, for flow inside the pipe, they wanted to know whether it's a laminar or not. That's for external flow. Okay, if you have a flow of, you wanted to see the left, for example, and also the drag. So there is a drag coefficient, there is a left coefficient, and all that. But for flow inside the pipe, they use the dye. Okay, they use the dye, so they can just observe the flow of air, or it's going in this direction. They could see that whether the motion is going to be uniform or laminar flow, or it's going to be turbulent flow, okay? And then between them, we call it transitional. So if Reynolds numbers based on this calculation came out to be less than 2100 to 2300, again, there is no units, and then we say the flow is laminar. And if Reynolds number was greater than 4000, it's known as turbulent. So that's a standard published value. Anywhere you go in this world, they use the same thing. And Reynolds number was a British engineers that came up with this formulas, okay, and these rules that still people are using his theory called Reynolds numbers. Okay, all right, so if Reynolds number between these two limits, the flow may switch between laminar and turbulent conditions. Flow that is on the onset of turbulence is called the transitional. Okay, so we're going to be talking about the average velocity, volumetric flow rate, viscosity, length of the pipe, pressure drop. Okay, so maybe this is very, very important for designing pipes that goes from one point to another point to deliver oil or water and or air. Okay, so we want, or natural gas, so we wanted to know how much per length of the pipe the pressure will be dropped, because you need to have a powerful pump to be able to push this flow to go to a distance. So the engineers wanted to see from where to where, from 1 kilometers or 10 kilometers, every 5 kilometers, every 1 mile, they have to put a pump. So to be able to help this flow to move through this pipe and to make sure it gets to the destination without so much drop, okay, pressure drop. So pressure drop is very, very important, okay? P1 minus P2, we call it delta P. And delta P in Bernoulli equation, we call the differences between the stagnation and the static pressure is equal to dynamic head, which was 1/2 rho V square in the Bernoulli equation. So, and this is for laminar flow. This is the volumetric flow rate. This Q is not heat transfer, okay? It's a volumetric flow rate. And that is a beautiful formula here, pi d to the 4th times delta P, pressure drop, divided by 128 mu, which is the viscosity, okay, times length. So that's a proven formula. We're going to use that. And from here, if the volumetric flow rate was given, we can find the pressure drop. Okay, we can rearrange this equation and solve for delta P. And then the other information is provided. And as an example, okay, as an example to see how we can utilize this formula, an oil with a viscosity of 4/10 Newton second per meter square and density of 900 kilogram per meter cube is flowing through a pipe with a diameter of 0.02 meters. It says we want to look at the pressure drop or determine the pressure drop delta P over a length of 10 meters. Just for the sake of, you know, understanding the language of pressure drop. So we pick a length of 10 meters is needed to produce a volumetric flow rate of Q, or that's, again, we switch from thermodynamics to fluid mechanics. So Q is no longer heat transfer, okay? It's a volumetric flow rate, which is a meter cube per second. That's 2 times 10 to the negative 5 cubic meter per second. All right, so fascinating. So that information is given. Moving forward, we want to, again, as we go through this lecture today, you will learn about the losses such as, you know, major loss and minor loss when we are dealing with the fluid flow inside the pipe. Okay, all right, so, and I'm going to go to here, and it says, based on known, we have a known information, and the since we know the volumetric flow rate, and the average velocity is going to be volumetric flow rate over per unit area. Since this is a what do we call that? The round pipe, the area is calculated by pi d squared over 4, and d is 0.02 meters, and the volumetric flow rate was given as such, correct? So far, so good. Why do we need that? Because the velocity was not given, so we need to calculate the Reynolds number to see whether the flow is laminar or turbulent. So we know the density, 900 kilogram per cubic meters. We know now the average velocity here, and then we know the diameter, we know the viscosity, so we find out the Reynolds number is very small, okay, 2.87, which is much less than the 2100 that is indicated. So therefore, the flow is laminar. This is the proof that if somebody said, how do you know the Reynolds number is dimensionless? This is what we do. The density is kilogram per cubic meters. Velocity is meters squared per second. And then the denominator is, and D is also meters, correct? And then the D is meters. So meter square is meter cube cancel each other out. So we have kilogram per second. But the viscosity is Newton second per meter square. Therefore, we can go here, we say, okay, that the length information cancel each other out. So kilogram per, let me see here, something is missing. No, we have meter, okay, so kilogram per second, because that is also gone, okay, so that is gone. So kilogram per second, and kilogram per second here, then we have a Newton second per meter square. Let me see if I can say this is, okay, there, all right, no problem. I'm trying to get this right, okay. So eventually this is kilogram, let me just keep it that way, right? So this is kilogram per meter cube. This is a meter square for the velocity, and D is the meters, and Newton second per meter square. So if I write this as kilogram, because this is a complex fraction, so I have kilogram meter square over meter second, okay, meter square meter second, and then divided by, or let me see, no, I will just.
Professor, I think the velocity isn't meters squared over seconds, it's just meters per second. And then,
okay, that's where the problem is. Thank you, man. I see where the problem. Yeah,
I think you multiplied the length and then the velocity right there, and that's where you got meters squared. So you can get rid of that red M.
Yeah. So it was correct. In my head, I just multiplied the length meters, so meter square. So we have 1 meter is in here. So we have kilogram meter per second, meter second, and then this here. So then what I did was, because it's a complex fraction, I said kilogram meter square on the numerator. So you just multiply this by that. And then you have a denominator, which is Newton second times meter second. So Newton is kilogram meter per second square, and then we have second square times meters. So then you cancel each other, everything out. So kilogram meter square, they cancel each other out, and therefore we call it dimensionless. Okay, all right. So if one day someone said, "Can you prove that the Reynolds number is dimensionless?" Which is that? Okay. So now back to problem, okay, example problem. So we wanted to determine the pressure drop for the 1/10 of a meters, or for 10 meters, I'm sorry, for the length of the pipe, which is 10 meters. So we have the delta P equals 128 times viscosity times length times the volumetric flow rate times pi divided by pi d to the 4. So you plug the numbers and you will find out that the pressure drop is about 20.4 kilopascal. So you do the calculation, okay? So that is utilizing that formula in this example, okay? So that goes here. Next, I just wanted to talk about the head loss, okay? Head loss. It's a little bit of tedious work, but we're gonna be able to get this under control, okay? All right, so head loss. We have two types of losses in fluid flow, internal flow. We have the major losses, okay, and then the minor losses. Major losses are due to friction, okay, and viscosity. So major losses is associated with friction or viscous flow effects as the fluid flows through the straight pipe and can be expressed as such. So this is a famous formula which is known as Darcy-Weisbach equation. Darcy-Weisbach equation, which is the friction factor, dimensionless, okay, that lowercase f, lowercase l, L over D, and L is the length of the pipe, D is the diameter of the pipe, and then we have the velocity square over 2g. So frictionless or friction factor is independent of the relative roughness and is a function of Reynolds number, okay, function of Reynolds number. So we're going to talk about or learn about a chart called Moody chart, okay? This is a Moody chart, okay? All right, so if you look at that, we have a region called laminar flow that's lined here, which is a function of Reynolds number. So this is proven that it's a, for laminar flow, the friction factor is 64 over Reynolds number. And also the Reynolds number, you calculate the Reynolds number to see where you are at, okay? You go from 1,000 to 2,000 to 4,000, 6,000, 8,000, or, and then you go to 100 or 10,000, okay, 10,000, and then 2 times 10 to the fourth, and so on along this x. So on this side, we have the friction factor. On this side, we have the ratio of the roughness divided by diameter. What is the roughness? Remember in circuit, if you have, if you want to calculate the voltage, voltage equals Ri. R is a resistance or of a resistor, which prevent the current to flow. So you want to know what will be the voltage drop across each resistor. So it depends on the size of the resistor, whether it's a 2,000 ohm or 1 kilo ohm and so on. So inside the pipe, we have not a smooth, if it's a smooth surface and somebody said that the inside the pipe is smooth, then we don't have the epsilon. That epsilon is 0 for a smooth surface, internal surface. So D is a diameter. So this side, we have the ratio of roughness inside the pipe divided by diameter of the pipe, which is a very small number. You can see that 0.0005, okay, 1, 2, 3, 4 zeros. So all the way goes up to 0.05, okay. So this region is laminar. Then we have a turbulent flow on this region, which is a function of surface roughness, okay? And that is this here, this curve here. It's for a smooth surface, then the friction factor is 0.316 divided by Reynolds number to the 1/4 of the power, okay? All right, so this is a very popular chart. It's known as friction factor as a function of Reynolds number and relative roughness for round pipes. This is called the Moody chart, okay? Moody chart. All right, so in the future, you're working on your senior project and you need to calculate the, the losses for the inside the pipe. So you need to refer to this chart called the Moody chart, okay? Anyway, so for time being, I'm gonna just put this aside so you know where that is on chapter 14, okay? Section 14.5. So I'm gonna move it to the side so we have some room to talk about these things, okay? All right, so, and this is the formula for major loss, head loss. And if it's a laminar flow, we have 64 divided by Reynolds number. For Reynolds number less than 2100, we call it laminar flow. And then to go to Moody chart, we said we need to have the ratio of surface roughness to diameter and the friction factor. So epsilon again is a roughness value. For a smooth pipe, we use this formula here. And I just showed you the Moody chart. Okay, no need to go over that. But if, again, if epsilon is 0 and it's a turbulent flow, so Moody chart, we go to Moody chart, we have the laminar flow, turbulent flow, and we have a smooth pipe, okay, for a smooth pipe. For a smooth pipe, epsilon is 0. Okay, so, and then in a problem solving, we might have a elevation, difference in elevation, Z1 minus Z2, could be the friction factor, L over D, V squared over 2G. Okay, so we're going to talk about that. All right, so this is a major loss. You might say, what is a minor loss? Because the head loss is a summation of major and minor, okay, minor. Minor may not be significant. In some situation, they just say negligible or ignore the minor losses, but not always, okay? It depends on your situation, your application, your design. So let me just go here and show you what the minor losses are, okay? Minor losses are due to sudden contraction of the pipe, sudden contraction, such as this, when the flow is entering a region, which is the sharp, you have a sharp edge versus the fillet radius or round edge. So K subscript L represent that the loss coefficient, okay? They call K subscript L, they call it the loss coefficient for pipe components using table 14.2 in your textbook. Component could be elbows, okay, elbows. So you have an elbow. So if you're designing the pipes for the sprinklers in your house and you have to get elbows, such as 45-degree angle, 90-degree angle, 30-degree angle, it depends on your design and how you want it to bend the pipe and so on. So this type of bend, we call it for elbows. You have a table in your textbook, and you can just and that table is table 14.1. Okay, table 14. We'll use table 14. This is
14.2 on page 321.
Okay, 321. Okay, 14.2. So that's a 14.2. So I was right, using table 14.2, all right? And page, thank you, page 321. So that is your, your resource, the table that you can go to. This is something that has been proven. Law of testing was done 50 years ago, 60 years ago. And we are just copying the work that was done, and they have done law of testing, and they came up with a loss due to the, say, for example, I'm saying regular 90, or it's a 90-degree flange, okay? That's a 90-degree flange. And you have the KL is 0.3. Okay? And for different component, you have different KL, okay? That's a KL, all right, so. And I'll leave it up to you to look that up, okay, in a problem solving, the homework, and so on. So you know where to go to find the KL. So for the sharp entrance, sharp edge, and the KL is 0.5. For well-rounded edge, entrance is at 0.04. Okay, let me get a little bit of water. I've been talking all day. All right. So for well-rounded edge, KL is 0.04. If it's the exit is going to be sharp when the flow is entering a larger region, then the KL is 1. And then for well-rounded, it's going to be 1 as well. Okay, so for these both cases. So please look that up. It's on page, again, this is KL. That will be on page, if I could find that the losses, it's on, okay, this is on page 321, okay? Page 321. Okay, anything you want for homework problems and exam, so you can go to this page. So I just wanted to cover that because I'm going to assign homework for chapter 14, and also I'm going to add chapter 15, but I might start on chapter 15 tomorrow, which is a heat transfer by conduction, convection, and radiation. But you can get started on the portion that is a chapter 14, so you know how to do the solve the problems for that. Okay, all right. So, and let me see if I have another example problems here. And that is okay. So instead of water, we have air. Okay, air flows through a horizontal section of 4 millimeters diameter drawn tubing. Okay, drawn tubing with an average velocity of 50 meters per second. So we want to find the pressure drop in a 1/10 of a meter length of the tube. Okay. Assumptions are these. Air model as an incompressible fluid because of the low velocity. Okay, low velocity, according to Bernoulli also, said that we can assume the air to be incompressible for low velocity. So the density remains constant. So that's a density of air at 1.23 kilogram per cubic meter. Viscosity is this. And we can look that up from the appendix called FM-1, okay? You go to the appendix in your textbook FM-1, you can find that information. Assuming that flow is fully developed, okay? And the minor losses is zero, okay? Assume that the minor losses is zero. We have only major losses due to the friction, okay? So then we use the energy equation, which you are all familiar with this here. And then in here we have a head loss also, and then let's see, plus head loss, correct? All right, so plus head. So we assume that the velocity entrance and exit are equal to each other because it's a straight pipe, horizontal section of it, and is only 1/10 of a meters of the length of the pipe. So it's not that far, that long. Okay, so the elevation is also equal, so we cancel each other out from the energy equation. So then we can just go to delta P, which is a P1 minus P2 over gamma, because these are all, cancel, okay, from each side. So we have a delta P, we cross multiply the specific weight is going to be times HL, okay, times HL. So a specific weight times the head loss, that is the one we are interested in. And the pressure drop is going to be, again, we can just substitute for head loss, which is, this is a beautiful formula for head loss, F friction factor times L over D, V square over 2G. So the G and G cancel from here, and then we have friction factor L over D times 1/2 rho V squared. This reminds me of what? This reminds you of Bernoulli, correct? Because Bernoulli said for incompressible flow, the delta P equals 1/2 rho V squared. And also we are multiplying the dynamic head by the friction factor and the length of the pipe over the diameter of the pipe. Okay, that's a fantastic formula. So we want to know the Reynolds number. Why we need to know the Reynolds number? Because we need to go to Moody chart, okay? Mr. Moody chart, we're gonna go and find the friction factor. Everything else is known. So Reynolds number, we know the density, we know the velocity, we know the diameter, we know viscosity. The Reynolds number came out to be 1.37 times 10 to the 4th, and it's a turbulent region. And then the surface roughness for this kind of tubing, you have to go and look that up in a table for the drawn tubing. This the roughness and surface roughness is given as 0.0015 millimeters. So for turbulent flow, we know that the friction factor is a function of Reynolds number and ratio of surface roughness over diameter. So that is there. Now, what do? We go to, we need to, one little, maybe a tedious work, We call it the Moody chart, okay? Let's just become familiar more with the Moody chart. So let me see, it says table 14. Table 14, can you, Matt or someone, can look that up to see for drawn tubing, we get the epsilon equals 0.0015. Table 1, okay, let me see. Okay. I'm just waiting for you guys to find.
Yeah, it's hard to, it's so small, it's hard to read.
Okay, so it's.
Yeah, I found the epsilon value of
0.0015. Okay, all right, so that, again, some of those numbers are very, very small, infinitesimal. But again, they're using epsilon in here in fluid, and then when we go to heat transfer, we call it emissivity. So that is denoted for emissivities, and alpha is absorptivity. So, but that's okay. We're gonna hang in there. We could say. So is this correct, Matt? This number here? Yeah. Oh, that,
yeah.
Okay. All right. Beautiful. So, and then this ratio came up to be 0.0030375, and using the Moody, okay, Moody chart, that's how it's pronounced, okay? I remember for the last 45 years, I've been just dealing with this, or I went through this thermal sciences for many years when I was younger. So I used to just knew the Moody chart, just I memorized a lot of this stuff, okay? But anyway, now if you go to Moody chart, if you have in front of you, you can do this, and you can have the Moody chart for on the right hand side we have 3 zeros. Okay, I'm gonna look for 3 zeros. Oops, it's so tiny. Okay, let me see. 0.00. Let me see if I can bring it down a little bit here. 0.00375. It's almost like 0.004. Is it 2 zeros or 3 zeros? Am I right on that?
It was 2 zeros.
Oh, 2 zeros.
So it's right in between 0.001 and 0.0008.
Okay. So this is not 3 zeros. This should be 2 zeros, right? This is not 3 zeros.
Yeah.
That should be, yeah. That's why I just detected that shouldn't be. Okay. So because the friction factor is 0.028, okay, wow, this is not easy not convenient here. Okay, so can you see on the left hand side here, 0.025, so somewhere here, so we have to go to 0.0037, so it's almost 0.004, correct? Can we just do that? And I have a ruler. Let me see if I have a ruler somewhere here. I can use ruler to when I always have a rulers around here, but not at this point. Okay, so if you have a ruler, you can just go and look at this side here, 0.00375 somewhere, and then you go across, and then you have to also have an intersection with Reynolds number. Okay, and the Reynolds number was 1. What was that one? We said the Reynolds number is equal to 1.37, okay, times 10 to the fourth. 10 to the fourth, 1.37. Okay, so this is somewhere maybe here, and then go up there, and then you go across here to the right, and then you get about 0.0028. 0.028, I'm sorry. So somewhere here, all right? So, okay, guys. You have very fresh eyes, and you don't have to worry about anything. So you can just use your rulers and then have this ratio ready, and then you locate that in here, and then the Reynolds number. So the intersection of the Reynolds number and that, it gives you the curve here. So then you go across and find out the friction factor. Say you found the friction factor, and then you come here back to the formula, then everything is easy. The only thing that was tedious was this here, friction factor from the Moody chart. So then you can report that delta P is equal to 1.076 kilopascal. Okay. How you doing, guys, so far? Okay, so that is my just a favorite, type of problems that I can see that because I wanted to show you how you can use the Moody chart. Okay, that is done. Let me see, this is, okay. I think that's good enough for today. I'm done with chapter 14, okay? So chapter 14 is done, and then we can, I can get started on heat transfer, but let's just wait until tomorrow to cover this topic of chapter 15, which is the 3 modes of heat transfer, which we call it conduction, convection, and radiation, okay? So I'll be lecturing on this. If you have some time, please review chapter 15. It's fascinating topic, like, you as a industrial engineer, mechanical engineer, electrical engineer, it's good to know how to calculate the flow, whether it's a conduction between 2 surfaces that is touching each other, or between a surface and fluid. And if you just have the tail of, or the spoon, if you put it in a hot water, you can see that the spoon is going to get hot. So, and then there is a Fourier's law of transformation. So we have the heat flux, which is equal to the negative thermal conductivity times the temperature gradients, okay? So times the gradients, dt dx. Because we use that in materials class, we call it the driving force for diffusion processes, whether we have a steady state diffusion or non-steady state diffusion of having copper and zinc, the atoms that migrates from one lattice to another lattice, we call it the diffusion, a steady state diffusion. So we on the driving force, we call it the temperature gradients, which is this here. So temperature gradients is dt over dx, thermal conductivity based on the wall materials, depends on the materials, the thermal conductivity. There is a table, we can look that up. And then the dt dx, we call it T2 minus T1. So if we have the temperature versus the x-axis, then we have a plane wall, and we have a T1 and we have a T2. So we call it also Newtonian cooling also. Mainly the Newtonian cooling will be for convective heat transfer coefficient, but we can also use for the wall that we're looking at the wall, so the temperature is going to decrease, okay, as from x equals 0 to x equals L, some length of the wall, L. And then a Q double prime, they call it a heat flux, okay, heat flux, which has a unit of watt per meter square. So conduction is when a temperature gradient exists in a stationary medium with maybe a solid or fluid, okay, with solid or fluid, which I just mentioned. Negative is indicating that the heat is transferred in the direction of decreasing temperature, okay, decreasing temperature. And the Q subscript X with double prime is the rate of heat transfer per unit area. We have heat, if it's a per unit length, we call it the rate of heat transfer, or just if it's just a Q, then we have just a transfer of heat, and then we multiply the right hand side by area, if we have a Q equals minus KA delta T, okay? Then you can write it like that. Okay, beautiful. But when you are indicating that the double prime in here means flux, okay, per unit, per square meters, okay, watt per meter square. All right, so I'm going to continue on this tomorrow. I'm going to be posting the homework for chapter 14 and 15. You can start working on chapter 14 of homework, and then tomorrow I'm going to continue on with chapter 15. And then on Thursday, I'll be reviewing, I will be just giving you some examples of chapter 15 and chapter 14, more examples, so you will be ready for Friday's final exam. Okay. Thank you guys for listening, and I'm going to stop recording, and that is, and this is going to be posted on Blackboard, okay, for those that was not able to make it.